This is Bob Capetto, and this lesson is on Venn diagrams, a way for us to visually represent sets. So let's start with this notion of a universal set. Typically, that is defined with the letter U or described by the letter U. These are all elements to be considered. So you're going to have different universal sets for different problems. So in this first example, I'm going to let the universal set be all the letters of the alphabet. A, B, C, D, W, X, Y, Z. And we typically note the universal set with a rectangle. So this represents all letters in the alphabet. And we put a little U in the corner to represent that universal set. Now let me define a subset A. The subset A will consist of the vowels little a, little e, little I, little o, little u. So we use capital letters to represent sets like U and A, little letters often to represent elements of sets. That's kind of the standard notion. And we use circles to represent sets. So we will call this A that is included inside the universal set. Now, what are the elements that are in A? Well, again, we have those 5 vowels, little a, little e, little I, little o, little u. Everything else that is not in A would be in U, would be outside of A in U. Things like B, C, D, not E, F, G, H, not I, J, K, L, M, and not O, P, Q, R, S, T, not U, V, W, X, Y. Well, I didn't put Y in the vowel category, so I'll leave it in the consonant category. Y, Z. So it's just kind of a visual representation of what that set looks like. So again, our universal set, all elements to be considered. A is a subset, a subcollection of elements in that universal set U. And all of those letters that are outside of A are going to be something called the complement of A that we will look at shortly. So we get our idea. So we looked at letters for our universal set for that first example. This time, let's let U be North American professional athletes. So we draw our U. Put it up here in the corner. That's our set U. And the set A will be NFL players. Now remember, a set has to be well defined. It has to be well defined. So let's say that these are players who are currently on NFL rosters, and we can draw that set A here. So either you're on a roster or you're not on a roster, so there should be no ambiguity. So anybody inside this cell are current NFL players. Anybody outside are pro athletes who are not current NFL players. B will say are Canadian Football League players. Now, over the course of careers, people may play in both leagues, but at one time, they cannot be in both leagues at the same time. So if that's the case, there is no overlap. Here is our set B. So, who would be in set A, who would be in set B, who would be out here? Anybody in the NFL is in set A. Tom Brady is in set A. Drew Brees is in set A as I am recording this. In set B, some Canadian Football League players. I'm sad to say I don't know any offhand. Out here, Major League Baseball players, pro golfers, tennis players, etc. These sets do not overlap. These sets are disjoint. Another term that we use is mutually exclusive or mutually exclusive. So if you have a situation where there is no overlap, right? There is no overlap. The sets are disjoint. They are mutually exclusive. You cannot be in both sets simultaneously. So if you have two mutually exclusive sets, it sort of looks like this. This is our basic appearance of the Venn diagram for two sets that are mutually exclusive. All right. This time, our universal set U will be university faculty. At Florida institutions. So we'll draw our box. We tend to use rectangles to represent the universal set. The set A this time is going to be University of Miami faculty. So again, it's a Florida institution, faculty. University of Miami has to be well defined, so people who teach and get paid to do so. It's how we're going to choose to define that. And this is our set A. Set B will be University of Miami music faculty. And notice, all of the music faculty at the University of Miami are also University of Miami faculty. So this set B sits completely inside set A. So we would say here that B is a proper subset writing it this way, B is a proper subset. I don't need the equal sign on the bottom of A. So our first case, we looked at disjoint sets. Our second case, we looked at proper subsets. But really, our most interesting case is when they overlap. So let's take a look at the following. This time, I'm going to let our U, our universal set, be the set of natural numbers. So let's say that. U, the set of natural numbers. So if you're not clear, U is 1, 2, 3, 4, 5, forever and ever. So again, our universal set is typically represented with a rectangle. And we put a little U in the corner. There's our universal set. Our set A will be all the even numbers. Now that's half of the numbers in U. So you might think, oh, I better draw a circle that is half as big as the area of U. No, you don't have to. The size of the circles in the Venn diagram do not represent the number of elements in the set. So it is sufficient for us to draw a circle about that size. So those are all the even numbers would be inside the circle, all of the odd numbers would be outside that circle. Set B are going to be multiples of 7. Now, you might think there's a lot more even numbers than multiples of 7. In reality, that's not the case. But that is a question for higher level math classes. I'm going to go ahead and I'm going to draw a B here. And you'll notice this is our favorite type of Venn diagram, and then we're going to have what? We're going to have some overlap. So even numbers are in set A, so 2, 4, 6. Multiples of 7 are in set B, like 7, but where does 14 go, right? 14 is both an even number and a multiple of 7. 21 would be here. But 28 would be here, and there's many, many more, right? There's many, many more. But again, you can see that we have numbers in each of 4 regions. Numbers out here that are neither in A nor in B. So they're not even, they're not multiples of 7. I guess 1 would be out here. 3 would be out here. 5 would be here. 7, not 9 would be out here. And again, a whole lot more numbers out in that direction. So those are the various kinds of Venn diagrams that we can have. And there really are 4 regions for us to look at. And we can count the number of items in each region. So this is helpful for us when we're doing some analysis. So let's draw a Venn diagram. Again, we start with the rectangle to represent the universal set. We're going to have a set A and a set B. This is our set A. This is our set B. But again, there's actually 4 distinct regions that we have in this Venn diagram. We have region 1. We have region 2. We have region 3. And we have region 4. Now, how do we describe these regions? I mean, how can we describe their location, what's in those regions? So region 1, what would that be? That would be values x such that x is in A and not in B. X is an element of A and X is not an element of B. So that's what's going to show up in region 1. Region 2, that's our overlap. Region 2, X such that X is both in A and in B. How about region 3? Think about that for a second. Region 3. Well, we're in B, but we're not in A. So X such that X is in B and X is not in A. And then region 4, it's not in A and not in B. So those are our 4 regions. X such that X is not in A and X is not in B. So that describes our various regions that we're working with. So let's go ahead and make a couple more definitions here about these various sets. So let me go ahead and introduce this concept of the complement of a set. So this time we're going to give our universal set. Again, the numbers we're considering, the items we're considering. In math, no surprise, a lot of times we like sets of numbers. So my set U is the numbers 1 through 10. My set A is 1 through 7. And I want to know, what is the complement of A? How do I find the complement of A? Well, the notation that is used is A, this, or sometimes A with a little c, depending on the textbook you're using. But the complement of A is defined as elements that are in the universal set X such that X is in the universal set and X is not in A. So you see complement, you're going to say what? You're going to say all those numbers that are not in your set that you're given. So in our example here, the complement of A will be what? Not 1, 2, 3, 4, 5, 6, 7. They're in A. What isn't in A? 8, 9, and 10. So if I wanted to draw a Venn diagram or identify where is the set complement of A, here's our universal set U. Here's our set A. Where is the complement of A? Anything outside of A, right? Anything outside of A would count as the complement of A. So if I'm shading the complement of A, that is what that is going to look like. Okay, our next notion is the intersection. What is the intersection going to give us? Before I give you the formal definition, let's think about the intersections of two streets. If I have two streets here, what is the real intersection of those two streets? So let's say this street is Main Street, and let's say this street is Park Street. The intersection of those two streets is this portion. And what can you say about that portion of those two streets? Is it on Main? Yes. Is it on Park? Yes. It's on both streets at the same time. So if you think about it, an intersection's got to be in both sets at the same time, and that's exactly how we define that. So the symbol that we use for intersection is this thing. And what is that set? That is the set such that X is in A and X is in B. X such that X is in A and X is in B. So if I have the following sort of question, I need to define my universal set. So let's go ahead and say the universal set is 1 through 20 this time. Just so we have an idea what we're starting with. The set A is going to be 1, 2, 3, 4, 5. And the set B is going to be 2, 4, 6, 8. We are interested in the intersection of those two sets. What does A intersect B? What is common to both of those? So you've got to be both in A and in B. That's how we're defining this. 2 is in both sets. 4 is in both sets. And it looks like that's it. So my intersection of A with B is just 2 with 4. Now, there's a couple other things we can say about intersection. Let's keep our same universal set from 1 to 20. If I have A is the set 1, 3, 5, 7, and I say B is the set 2, 4, 6, 8, what is the intersection of A with B? To be in the intersection, we've got to be in both sets at the same time. What numbers, what elements are in both sets at the same time? There aren't any. It's just the empty set, or if you like, if you prefer this notation, a set with nothing in it. It's not 0. We do a circle with a line slash through for the null set, remember. This represents null set or empty set. Is our standard definition. So let's take a look at the intersection of these two sets. What if I have A, 1, 3, 5, 7, intersected with the empty set? So what items are common to both sets? Now, this is going to seem a little strange, but the answer to that is, indeed, the empty set. Any set intersected with the empty set will always equal the empty set. So you've got to think that the emptiness is there always, almost a philosophical kind of idea. But that's in essence how we're going to play with that concept. And we've got one more thing to look at, and that's our notion of union. So let's give ourselves an informal definition of union first. before we give ourselves a formal definition. Union. So I like to think of labor unions. You might have Teamsters. So who are in the Teamsters? Well, you might have truck drivers. You might have dock workers. You might have some teachers and other sorts of groups. So to be in the union, you need a job. You could be a truck driver, you could be a dock worker, you could be a teacher. What if you have two jobs? What if you're a truck driver during the week and a dock worker on the weekend? Are you in the union? I think so. So it's a collection of everybody. So the symbol that we use for union is this. And this is the set of X such that X is either in A or X is in B. Now be careful. In mathematics, or means one or the other or both. One or the other or both. In English, when we say or, oftentimes we mean exclusive or. So if you're going to say, I'm either going to go to work or I'm going to take a nap, you're sort of implying you're going to do one but not do both. In math, if I say I'm going to go to work or take a nap, if I do both, I'm still telling the truth. So understand that subtle difference that we have in terms of mathematical definition of or and the standard language definition of or. So let's take a look at one quick example of unions. So we'll take our universal set again. We'll make 1 through 20. Seems like a good one to use. It's always good to know where we're starting. Let's say our set A, again, 1, 2, 3, 4, 5. And B is a set 2, 4, 6, 8. So which items are in the union? Which items are in A union B? Which items are in one or the other or both? Well, 1 is in one or the other or both. 2 is in both, that counts. 3 is in the first one. 4 is in both, so that counts. 5 is in the first one. Anything else? Well, 6 is in the second one. 8 is in the second one. So those are all of the elements that are either in one set or the other set or both. And that will conclude this lesson.